Hello, my name is Krish Gandhi, and this is Lab 1. So first, the purpose of the lab is we're trying to investigate how daily objects like a clear tape acquire an electric charge, and we'll use like simple assumptions to see that. We look at the relationship between electric forces and gravitational forces and connect observed behaviors to the fundamental rules of electrostatics. So key concepts here is we're looking at the second law of motion, which is mass times acceleration, the gravitational force, which looks at the relationship between mass acceleration and direction in a gravitational field, and then the electric force, which is the electrostatic force based on the two charges and the Coulomb constant. So here are a bunch of formulas that we will be using in this lab. Okay, so the experiment assumptions. So in the experiment, we are preparing charged pieces of tape and we're looking at the interaction and see how much excess charge is found on one piece of the clear charged tape, and we're going to try and predict the electron count. So the assumptions of experiment coding is we're acting like tape is a point charge at the center of mass, and assuming air resistance is ignored, and we're looking at how both tapes have the same amount of charge. So the system is the U-tape, surrounding is a base tape, seen in the image. Expectations is two pieces of charge tape would repel because like charges repel. And then observations that we saw for any neutral charge object attracted to U-tape. And then there was two charged tapes that did repel each other, and tape attract, and tape is positively charged. So in our experiment, these are the initial conditions, the gravitational force, and the electrical force that we saw, and the electron deficit. Here's all the formulas. Okay. So here is more results and calculations. So basically, we're looking at the number of atoms in tape. We looked at the area of the tape, the area of the single atom, and the number of the atoms, which is seen by the formula area of tape versus divided by area of atom, and we substituted values. For example, the number of atoms. And then we saw the ratio of electrons to atoms by looking at the number of electrons and the ratio of electrons to atoms through another formula, which is number of electrons divided by number of atoms. And then we substituted values as shown there. Here were some of the pictures that we used from our lab. As you can see, the left side is like when we stuck the tape together, and the right side is when we put it on the table. Here was some of our code from the digital portion of the lab. As you can see, it did work, and it showed the charge that was needed to flow on the tape that is above the other, which is 1.63 times 10 to the 9. Similarities and differences. So our observed calculated charge was 1.587 times 10 to the negative 8. Our computational charge is 1.9 3 times 10 to the negative 9. So they're pretty close, but still different. And some assumptions we made in the computation model was, again, negligible air resistance and friction, and the tape is represented by a point charge. Observations, assumptions was each tape has the same amount of charge evenly distributed. So in the discussion for the what if question, we said observations wouldn't change, and said there'd be a loss of protons instead of electrons, but attraction rules still apply. And for the why question, we said that it can lead to loss of charge of the tape and redistribute the charge. So for our lab questions, if the U tape was positively charged, it would repel, because it would attract the pen if it's negative, and then you would see vice versa if it was negative. If U tape was neutral, it would be a charge to the plastic pen because it would induce an opposite charge. And if you rub the pen on cloth or air, it would give a negative charge to the pen. Here's 8.1 questions. Here's our answers to them. And then errors, inconsistent tape pressure, preparation, measurement, environmental, and misidentifying tape. And that's it.